I'm now recording. So it's my pleasure to welcome Yuval to the Cybersecurity Bootcamp. Yuval's been part of the group now for a couple of years, and we had you over in Tallinn in 2016. 2017, for some reason, we didn't know where you were, but now we do know what you've been up to. So we've all heard, I think, about Spectre and Meltdown, but now it's time to hear what's really going on. So thanks, Yuval.
Thank you for the introduction, and thanks everyone for coming to listen. This is not my work. It's a joint work with quite a lot of authors. These issues were discovered by 5 groups independently, and we just joined forces instead of trying to race and see who gets this published first. So, summary of our results. We have 2 different attacks. One is called Spectre, that exploits a design flaw in most modern processors. And basically what the flaw is that when the processor does what's called speculative execution, I'll go over that in a minute, it leaves some traces, and we found a way to exploit those traces, or to look at those traces and understand what the processor was doing. The second one, Meltdown, it also uses speculative execution, but the main thing there is that there is a bug in Intel processors and in some ARMs, and the result is that the user can bypass the memory protection. So there are pages that are not readable, the user can read those. What we can do with that is we can read any location in the kernel. For example, user space can read any location in the kernel address space. And because the kernel maps the physical memory, that means that we can read everything that is in the physical memory of the processor. We can read everything that exists in other programs' address spaces. We can bypass language-based security. So a JavaScript code can read everything that is in the browser's process memory. So. Now, the whole thing is based on exploiting what we call microarchitectural channels. And if we have some assembly code, this is taken from the implementation, I think it was RSA in OpenSSL. And the code, when we think of it, it executes commands one after the other. And while it executes, it leaves some traces in the processor, because it changes the processor state. And as it continues to execute, it leaves more traces. And if we monitor these traces, we can understand what the program is doing. Now, this area of research has been active for past 15 years. First attack was disclosed in 2002. People were showing how to look at the processor state and understand what programs were doing. It gained some more popularity in recent years. Since 2014, this is a very active area of research. Many of the people that were involved in this discovery are right in this area, because that's where our attack works. And basically, what we get here is some communication channel between the program that executes and our spy that listens or that looks at the traces. And we distinguish between 2 types of channel. And covert channels are channels where we have a sender, so the machine code, the program that executes and leaves the traces, does it intentionally. It just makes sure that the traces appear in the processor. And then we get a communication channel that the operating system, for example, cannot control, because this is not part of the communication channels that the system knows about. The other type of channel is what we call side channels, and these are inadvertent channels that just happen, that the spy happens to exploit the traces that are left by the program, but the program does not intend to do that. And until last year, from security perspective, side channels were considered a real security threat, and covert channels were something that was for military systems, that we don't want to leak information between things that run on the same machine. And with side channels, we did attacks that grabbed the cryptographic keys, and we find out user activity, and we see what web pages users do, and kept publishing about that. So now, what do we mean by having traces in the processor? So let's look at an example. We have a processor, and we have the memory. And as you know, processors have become fast in recent years. The processor doubled their speed every 18 months. And memory also became faster, but not at the same rate. So we created a big gap in speed between the two. And when the processor wants to read data, it takes some time for this data to come from memory to the processor before it can do anything with it. And because we write programs and programs have locality, it usually happens that if we needed some data, we'll need it again, and then, unless we have other measures, we need to wait again, and that takes a long time. It takes a long time. That means the processor sits waiting for data instead of doing the work that we want it to do. So what processor designers do is they add a small bank of memory that we call the cache between the processor and the main memory. And this bank is a different technology. It's more expensive, but it is faster. It is smaller, and when the logic is smaller, it is faster than larger logic. And it is closer to the processor, so signal propagation is faster. And what happens, the cache works at almost the speed of the processor. So what we can do now is that when the processor accesses data, the cache captures the data on the flight, and the next time the processor needs the same data, it gets it much faster. And that's beautiful, and it works, and our processors wouldn't be as fast, or our programs wouldn't run as fast as they are without these caches. But the fact that this location is in the cache gives us some change of state that tells us which location the processor has accessed. And this is the type of traces that we then exploit. Okay, so now let's look at the way that processors execute commands. So we have our assembly code, and the way that we think about assembly code is, or it doesn't really matter, the way we think about programs in general, is that we have a sequence of commands, and the processor does the first command, and then it does the second command, and then it does the third, and continues this way. So basically, we think of it going sequentially over the memory. Now what happens is that when we look at instructions, they have several steps. So for example, we can divide the execution of instructions to 5 steps. This is the example here. In real life, processors now divide that into 30 or more steps. But these are the steps that we'll use for the example. So instruction fetch gets the instruction from memory. Decode, understand what this instruction is supposed to do. Argument fetch gets the argument that we want to operate on. Execute does the operation, addition, multiplication, whatever. And write back, put the results wherever we want the result to be. And then the processor does its first fetch instruction and continues executing until it completes the instruction. And that's nice, and it works, but the important thing is that each of these steps require a different unit in the processor. So what we can do, instead of waiting for 5 cycles, 5 operations to execute a single instruction, we can start doing things in parallel. And what we do, we increase our utilization by just executing, making sure that each of our units is busy. So we start the first instruction, we fetch it. And then we decode the first instruction, and in parallel, we can already bring the second instruction from memory. And then we can continue execute things in parallel. And the beauty of that is that effectively we execute an instruction in one cycle instead of waiting 5 cycles for each instruction. And graphically, we have such an execution, some instruction partially executing, and this progresses through memory and through the program until we execute the whole program. But this model has some problems. And one of the problems is dependency. So suppose the first instruction does a division of 2 variables, and the next one adds 5 to the result. What happens is that we cannot start fetching the arguments for the second instruction before we have completed the first instruction. So there are several solutions to that in processors. And the simple way is to wait until the results are available, but that's a waste of time. So high-end processors, and that means almost every processor that we have except for processors in Raspberry Pis, that means that we execute what we do is we execute instructions out of order. And how does that work? So we have an example here. We start fetch an instruction, continue the same way as earlier. Now we need the arguments for the second instruction. And the arguments have not been computed yet, so we don't know what they are. So we stop the execution of this instruction, but we continue everything else. And then the first instruction completed. Now we can continue with the second instruction, and we go and continue executing this instruction in some order. Now what happened here is that the third instruction finished before the second one, because it doesn't depend on data from the first instruction. In this case, what the processor does is wait. It tells this instruction, you wait, you don't write the result, you don't really write the result to memory or to register or whatever, until the previous instruction completed. And when the previous instruction completes, both of them will write the results, and everything can continue working as before. And again, graphically, what we have is we have two fronts. One that tells us where our execution is, where we start executing instructions, and the other one, the green one, tells us where we have completed the execution, all the instructions until that position. And they progress, and this progresses along our program. So we have in the orange area, we have some instructions that are in partial state of execution. Now, an important question is, why do we wait? Why don't we retire the instruction immediately when we finish it? And the answer to that is that there are some dependencies that could cause a problem. So for example, if we look at this state, assume that calculating the division takes some time, and in the meanwhile we finish the addition at the bottom. And we try to retire the result, so we change the value of E. What happens if now we find out that B was 0? If B was 0, then the first instruction shouldn't have completed. We should have got a trap. The processor would get us to handling the trap, and the following instructions just wouldn't execute, right? If we have retired the third instruction, we would have created a state that cannot execute under the way that we think about instructions being executed sequentially. So that's the reason that we wait with committing to these results until everything earlier has executed. But what that also says is that whenever we have out-of-order execution, this is basically speculative. We execute the instruction believing that the previous instructions are going to complete correctly. If they don't, then we started something that we shouldn't have started. Now, first, what do we do with this speculative execution when we found out that things went wrong? We found out that B was 0. We just abandoned all of these instructions. We say, this hasn't happened. We throw the results. We don't care about that, and the program continues wherever it's supposed to continue after a trap. Now, so this gives us the mechanism of handling traps with out-of-order execution. And then the other thing that it helps us is with handling branches. What are branches? We have a program, and at some stage it reaches the location that it can choose two different ways. Either we take the branch or we don't. So, again, we go with our execution, and the front that start processing the instruction, it reaches the branch. Now, what should the processor do in such a case? There are two options. One is wait until we know what the condition is and what the result is and take the right direction. But that's waste of time. We waste resources. And this orange area can be 200 instructions long. So we need to wait 200 instructions now until we can decide whether we go to the right or to the left. Now, the processor doesn't know where we are going to go. So what does the processor do? It asks a fortune teller. And the fortune teller tells the processor which side this branch is going to go. And that's beautiful. The processor tells it to go to the right, and it goes to the right. And then at some stage, execution catches up, and we know where the branch is supposed to go. And obviously, we're working with fortune tellers, and sometimes they're right, and that's beautiful. They were right, and they will tell everyone that they were right, and they will get new customers. And we got much better performance. Sometimes, unfortunately, fortune tellers are wrong. What happens then? They blame the environment. They say that they were misunderstood. But for our perspective, what we do is we abandon that execution and continue in the right branch. And the good thing the reason that we can do that is that at the bottom line, what we compare our execution is to what we would have done had we waited. So had we waited and then a misprediction means that we have done some computation that we don't really care about, but we did not get a performance that is worse than having to wait. And if the prediction was right, then actually we gain performance. So there is nothing to lose in this case. Technically, and processors work hard on these fortune tellers, this whole area of branch prediction, and currently Intel claims that they are 92% of the time they are right. It sounds like very good percentage, right? 92% right is much better than random guess. Think about a loop that goes 1,000 times. If we just guess that it will go back to the beginning and not, then we'll be 99.9% right. So 92% now is good performance, better than guess, but they probably might be able to do better. Anyway, the processor has two types of fortune tellers. One fortune teller is looking at the history of the branches, whether the branch was taken or not taken. So we have a conditional branch. Condition can be true or false, and if it is true, the branch is taken. If it is false, the branch is not taken. And we have a fortune teller that tells us whether to go there. That's called the branch history buffer. There are a lot of algorithms, and we don't really know what Intel does there. There are some papers that try to analyze that, but they manage to predict whether the conditional branch is taken or not. The other type of fortune teller is the branch target buffer. This is used for indirect branches. So branches that take an address from register, this is an example. We use those to implement switch statements in C, for example. Calls that takes an argument, that takes the argument from a register, we use that to implement virtual functions or function pointers. And return statements that take an address from the stack, and we just use this address to branch back to wherever the call was from. So on these cases, what Intel does is remember that the branch at this address, last time we used it, go to that address, and therefore we believe that it will do that again. So we have two types of branch predictors. This is background, how processors work. Now, what is our main discovery? We have our execution models, and in all of those we have some possibility of abandoned instructions. And what we found out is that these abandoned instructions leave traces on what they were doing in the processor. So we developed techniques that exploit these. And Meltdown exploits the behavior after a trap. Spectre exploits the behavior of misprediction on one of the branch predictors. And we developed techniques to cause these mispredictions and to get the data out of what happens, out of these traces. So how these attacks look, we have very simple, well, we have a common attack scenario, and then we'll go into details. We have an attacker that is unprivileged in the sense that it does not have access to some data. And the examples that we have is user mode code does not have access to kernel data. Or one process does not have access to the address space of another process. Or a Java code has only access to the Java variables under the semantics that they have and does not have access to general access to the Java virtual machine address space. And now we have an attacker, and this attacker looks for something that we call a gadget, which is a short piece of code. And this piece of code, we need some conditions. So the attacker can control the input to this piece of code, so it can give it some values to begin with. It can cause speculative execution of this code. So it doesn't need to be able to cause the processor to actually execute this code with these inputs. It's enough that this is speculative execution with these inputs. We want that this gadget accesses data that the attacker cannot access normally when given these inputs. And we want this gadget to leave traces telling us what this data was. So this is a generic way that the attack works, and all we do once we find the gadget is execute it with the right input speculatively and check for the traces. So let's see an example how Meltdown works. So the typical code for Meltdown is 2 lines. We have dereference a pointer, and then use the value that we got from that pointer to access an array. And our gadget in this case is this line. Typically, this will be done in assembly because it's much easier to do these attacks in assembly, but we can look at that as if it is C. And first, look at what we try to understand is how this code executes under the normal conditions. So we have an address space of a program in Linux or in most operating systems, and up to January or up to late 2017, some early 2018. The address space consisted of 2 parts. One part for the user program, so it's the user program and the user data and the libraries that we use and whatever. And one part for the kernel. And this part for the kernel was marked only accessible to code that is running in kernel mode. So the user cannot access that. And now we have our pointer, and that pointer points somewhere within the user's address space. And we need to see what happens in the cache. And we assume that the pointer and whatever it points to are in the cache. And what more important, we assume that the array is not in the cache. Okay? That's the scenario we start from. Over the last 3 years, we developed techniques to make sure that things are in the cache when we want them, and they are not in the cache when we don't want them. So this is easy to do. It takes some practice, it takes some engineering, but we can do that. And now we start executing this code. So basically, dereferencing the pointer, we get the data here, and then we look at the array. So this data tell us where in the array we point to, right? And what this does is bring this data into the cache, because we need to read the data, so it will go through the cache, it will stay in the cache. And we're done. Simple. Questions on that? Okay, beautiful. That's the way that we expect things to work. So now we'll go to the attack. In the attack, what happens is that instead of the pointer pointing into the user space, it points into the kernel space. And again, let's look at our program. Again, we assume that whatever we point to is in the cache. Array is not in the cache. And let's look at the program. The first thing in the program is dereference this pointer, right? The same as before. Now there is only one catch. This instruction should not complete successfully, right? Because we are accessing memory that is not readable. But as it happens, while we are not accessing, we cannot access this, at the time that the processor does the verification that, or test whether we can access or not, it also brings the data. Why does it do that? Because it wants to save time, right? Otherwise, it needs to save for each instruction. It needs first to check whether we have access and only then fetch the data. So it brings the data and does the test. So it takes time. While this takes time, we also execute the second instruction. And for the second instruction, we take the data that what the processor does, takes the data from the kernel, points to the array, and this brings something from the array into the cache. A few nanoseconds later, the processor realized that something went wrong, abandoned all the instructions that were executed there, sends a trap to the process. We catch the trap and continue executing. And there are several ways we can catch the trap. And what we do now is we have our meltdown process that does the following. It reads the first location from the array and measure how long it takes to do that. And that takes a long time because we need to bring everything from memory into the cache and then read that. And because it took a long time and we measured that time, we know that it wasn't in the cache. So that's nice. We then do it on the second location in the array. And again, that takes time. And we read it, and we know that that wasn't in the cache. And then we do it on the third one. And this is fast because it is in the cache. And what does that tell us? That tells us that this is the address that we brought into the cache because of the speculative execution of the second line. And that, in turn, tells us what was the data that we were not reading from the kernel. Okay? So now we know what the data was, and we can continue to the next byte in the kernel and proceed this way. It is not that easy. There are several technical challenges that need to be overcome, but this is the outline of the attack. The rest is really engineering. So this is one. Second attack, Spectre, it has two variants. We look at one of them. We look at both of them, but we'll start with the first. So we have two processes. Or we look at that as two processes. Later, it can be a single process with Java code. With C, we have two processes. We have our attacker, and we have our victim. And this is a sort of code that we have in the victim. And the victim, what it does, this checks the input that user provides, X in this case, is within the bounds of the array. And if it is, it gets the data from the array and then gets something that depends on this data. Okay? And this is a very common code. So almost all array accesses we will have checks, or array accesses with input that comes from users. We will have these tests, because if we don't have them, then we have much bigger problems than Spectre. And if we write it in C, then we'll have these explicit tests. If we write in Java, then Java will insert that code when it creates when it compiles the bytecode. So this exists in most programs, and it's easy. Our gadget is these two lines. And what we do now with this as an attacker, we execute this. Okay? Attacker calls a function, sends a message to the process, whichever way that we have to do that. We need some control, some attacker control here. And again, we look at our memory, and what happens here, we have the two arrays. We have some secret data that the attacker is not supposed to be able to read, and all the rest of the variables in the address space. And the first thing we do is compare these. And then we use the value of X to point into array. Whatever we read from array points to the second array. And it works. And the beauty about that is that once we execute that several times, our branch history predictor learns what happens in its branch. It learns that X was smaller than array len, for 5, 6, 20 executions. And it learns that, so it knows the branch is not taken. So now is the time that we start our attack, after she has learned that. So to do our attack, we will again need to monitor the behavior of our cache. We assume that we have the secret in the cache, and we assume that we have X in the cache. And we do another call to this code. But this time, we use a very large value for X. So the first thing that is done, we need to compare these two. Now, as you know, array len is not in the cache. So that means that we need to bring it in from the cache. And that takes time. It takes time. The processor doesn't stop when it takes time. So this starts coming from the cache. The processor waits. It doesn't wait for that. Instead, it consults with our branch history, our fortune teller. The fortune teller tells him, you go, hey, to continue. The last times we got into the, we did not take the branch, we went into the instructions inside. So what it does is use X to index array, but because X is large, it goes beyond the bounds of array, goes into secret, and gets this data, indexes array 2, and that brings this into the cache. Okay? Now, at some stage, array len will get back to the cache, and we'll see that, oops, we had a misprediction here. And it doesn't really matter whether this happens before or after array 2 is cached, because once it started going into the cache, it will get there eventually, or sometimes it will get there. In other cases, it will not. But sometimes we will get it there. And at this stage, everything is reverted. All the instructions are abandoned. But we have our trace. We use the same method or similar methods to do the attack on this location and find out what the victim brought to the cache. That's the second variant, the first variant. Second variant, we have, again, the attacker and the victim. And we look at their address spaces. There are two processes running. We have the victim address space. We have the attacker address space. The attacker has an indirect jump. And excuse me, my Intel syntax or ATT assembly syntax is wrong, probably. But the important thing, we have an indirect jump, and we have a gadget. And the gadget basically does in machine code whatever we did earlier. We take data pointed by one register, in this case RBX. We take the data into AX. And then we use this data to index another array that is stored in this case, in register RCX. And this can be anywhere in the victim's address space. And now what the attacker does, at the same location that we have the jump, the attacker does, let's take the address of this gadget from the victim address space. This is just a number. It's not an address that the attacker can access. And do an indirect jump to it. And in that address, in the attacker's address space, we have some code, for example, returned from a subroutine, or anything else, or we don't really need code there. The instruction can fail, the jump can cause a trap, we catch the trap and continue doing it again. And what our attacker does is execute this. So it has load the gadget address, does a jump to the gadget location. And then it does it several more times. And after some time, even the stupidest fortune teller will learn that. What it will learn is that here, whenever we get to this location, we jump to the location of the gadget. And once that happens, we can start the attack, the actual attack. What is the actual attack? We cause the victim to execute this jump. Now, this jump does not have to go to, we don't care where the victim really wants to go with this jump. It could go to any other location in the victim. It usually will not even go to the gadget. There is no reason for it to go to that gadget. But when the victim gets to execute this instruction, what the processor sees is that this is what our fortune teller says. Let's do that. And from this stage, we got the same problem that we had earlier. So our victim goes, execute a gadget. This gadget leaves our traces. We can read the memory. So this is the second variant of Spectre. Now, what do we do against those? Intel and others came up with a few countermeasures. I'll describe the ones that Intel has, or that Intel suggests. So let's look at Meltdown first. We have this format of address space, this layout of address spaces. What Meltdown does, the fix for Meltdown, it's called in Linux, it's called KPTI. All the operating systems do something very similar. Instead of having a single address space, we have one address space that the process uses when it runs as user, and a different address space that the process uses when it runs as at kernel. And the kernel has the mapping of the user, but the user doesn't have a mapping of the kernel. And that's beautiful because now code running here within the process cannot specify addresses in the kernel. They have no meaning. It can only specify addresses within its virtual address space. The problem with that is that it introduces overhead. Whenever we switch from user mode to kernel mode, execute any system call, it takes time. And this time translates into performance degradation. How much performance degradation? Home computers typically lose 2 to 3%. Servers, if they are running a lot of I/O, a lot of system calls, can lose 30%. And then you start seeing questions. People write, oh, since Amazon installed the new patch, we lost 20% performance for our server. Who is going to pay for that? Okay? Now, who is going to pay for that? Unfortunately, it's the customer. But that means that Intel got a couple of class actions waiting for it to handle. So this basically solves Meltdown. So we have a protection against Meltdown. What about Spectre? For variant 1, we look at this branch, and we know that at some stage we have some instructions that leave traces. And what the compiler does when it builds the program, it looks at this, finds where the traces start coming, and insert an instruction that basically blocks speculative execution. The instruction on Intel processors is elfence. It was not designed to block speculative execution, but it happens to do that. And then what happens when we execute and reach this block, we don't continue with the speculative execution. So once we get to the branch, we revert, abandon everything, but we never executed code that leaves traces beyond with speculative execution. Now that's nice, that blocks the attack. It does have a problem. If we put barriers at every branch, that's expensive. We basically remove all the advantage of speculative execution. So what we want to do is to put barriers only in branches that the user can control the input and that leave trace. And Intel tells us use static analysis to find potential leaks. What does it mean, use static analysis? It means you run some code that looks at your assembly code and tells whether it thinks that it's going to leak or not. This is implemented in LLVM. It's implemented in Microsoft Visual C. It will probably be implemented in GNU CC soon. So we have a solution. The problem with that is that every time you block speculative execution, you lose performance. So we want to be aggressive with our static analysis and remove these elfences as much as we can. But if we remove one too many, then we are open for attacks. And if we are allowed to speculate in a talk like that. I believe that this is going to be a nice area for research. We're going to see bugs of these branches left unprotected for many years to come. It's the equivalent of a buffer overflows that we have for the last 20 years. So this is their solution. Another problem with this solution is that it doesn't work for legacy software. We need to rebuild all our software. We need to recompile everything and run it. And some of these software packages, if you change anything in the layout, they stop working. So it's going to be a lot of fun. Variant 2. Solution for variant 2 is very simple. Give each process its own fortune teller. The way that Intel does it, they issued a firmware patch for their processor. The firmware patch allowed the use of registers that were not in there before the patch, and they prevent learning from one process to affect another process. They have some beautiful names with 4 letters that do not mean anything unless you really read their documentation, so I'll just give the description of what they do. One of these control learning of BTBs between hyperthreads. So the branch target buffer is part of the core, and until the 3rd of January, it was shared by both hyperthreads that are on the same core. Now we have an MSR that tells the processor do not share them between hyperthreads. So program that runs on one hyperthread cannot teach the branch target buffer for another hyperthread. So that's blocks things that execute concurrently. Now, the second thing that it does, it divides code into security level, kernel versus user, for example, and says that higher security code does not learn from lower security execution. So when we cross from user mode to kernel mode, we cannot affect the behavior of branches in the kernel. And that's nice and it works. And then it leaves only one problem. We have one process running, context switch, another process running. So to solve that, they introduced BTB clobbering. It just removes everything that the branch target buffer knew, and we can continue with the new process. So Linux implemented that, and now there are discussions on trying to not do it every time, because it turns out that this instruction takes between 5,000 and 10,000 cycles. Okay? So, so now they're trying to look at things that saying that this process does not really leak information, or it's this binary, it's a flag on the binary. This binary does not really leak information, therefore we don't need this protection on this binary. Now, which binary doesn't leak information? Does cat, the one that cuts file, leak information? Well, if it runs with a sensitive file, then yes. What about Perl, the language processor? Well, it depends on what we execute, yes? We need to protect it if we ever run Perl on some sensitive data. So bottom line, we'll end up with some user processes might not be protected, but every system program must be protected, so we did not gain anything from this flag. So that's basically it. The last interesting thing is the people responses or companies' responses to these bugs. I'll let you read that.
This is brilliant. Did it take, I think it took like 2 days after announcing of Meltdown and Spectre until this one came out?
Yes. Yes. And actually, the release of those was a week earlier than we planned to. And the reason is that people saw that there is a patch going in the kernel, Linux kernel. And it was a big patch. They knew it was going to harm performance. The explanation was the original patch was designed to protect what's called kernel address space layout randomization, which is some sort of security feature, but it's not that important. And no one understood why Linus is pushing this patch out. So people start talking, speculating, and then a nice AMD engineer decided to push a patch to Linux that says AMD processors do not need this address, this KPTI patch, because we do not leak information of during speculative execution. That appears, I think it was the 1st of January, something like that. That appears. The day later, an exploit was on the web. So release was pushed by a week. It means that we spent the last 2 days writing a paper that was supposed to come out a week later. Questions?
I can't help thinking that your patches around Spectre in particular, by analogy, are now like identifying the best possible targets by looking for the best protected part of the code. So now it's, yes, it's protected, but it's also a big red flag to say this people.
You just use their code to figure out where to attack other processes, right?
Yeah.
Yep.
Yeah,
I see that as big. We've got time for questions, and lots of questions, I'm sure. Please.
Intel seem obsessed on taking every sort of side channel attack that we do and saying, oh, no, it's fine. Our processes are still correct with respect to execution. So, which is true. But I mean, obviously they're leaking information, right? The question is, what steps can Intel take to actually solve all of these side channel attacks?
Well, the first is the question whether they can take any steps to solve all these side channel attacks. In separate research that we have done, we tried to see whether we can close all covert channels in processors. And it turns out that if you wipe the cache, wipe the branch predictor, disable prefetching, and do basically whatever we can do, we still have channels. We don't know what the source of the channels, but those are enough to transfer data between processes. And the thing that we need, what we think we need for real secure programming, we need some guarantees from processor designers about the behavior of the processor. We don't know what the processor does. We don't really know what the algorithms that decide what data goes in the cache and what data goes out of the cache. We don't know how the branch target buffer works. We reverse engineered, but these are, well, we believe that this is what it does, but Intel never guarantees. So all of these things need to be open if we want to be able to design. For most of those, we can find ways around the problem, but we need to know what the design is, and we don't. And Intel, at least until now, did not have any motivation to look at security. What they were looking is to get the processor as fast as they can, and not as secure as they can. So in that respect, probably RISC-V is the most secure processor that we have, because at least we know how it's built.
Are there any implementations of RISC-V that don't have side channels?
I don't know. And the question is not whether they have side channels, whether we can write programs that do not leak on them. Yes?
So when did you actually advise Intel of this issue?
It depends on who is us. Google advised them in June 2017. We advised them in December.
At the moment, all the Intel processors are still vulnerable of Spectre. They need a proper hardware patch. So we could exploit them at the moment.
Yes.
Okay. How easy is to exploit it in JavaScript?
Okay, for JavaScript, the basic exploit is relatively easy. It takes several days to develop it if you don't have the code. There are some touchy points there, and measuring the cache is not easy. The problem with exploiting it in JavaScript is that all major browser providers removed high-resolution clocks from JavaScript, and without high-resolution clock, it's much more difficult to measure accesses to the cache. So that's one thing that they have done. And the other thing that they have done is to ensure that every page and every iframe execute in a different process. So you can leak information on the execution of your JavaScript, assuming you bypass the problem with the timers. And it can be done. We know how to do that. But even if you do that, you still only leak information about the execution of your own domain. So that's less significant. The leak is not that big. Yeah?
So Google advised Intel about this Spectre in June, and they have now come up with their own patch. Considering that Intel does not release their architecture, do you think, and they keep saying that their version is better than Intel's, so do you think we should trust them?
I think that it is a promising research area.
Do you have any further project about this topic?
There is a look. What we found here is we found that there is a problem. There are a lot of things that now need to be done. For example, in Spectre, there is no exploit. There is a proof of concept. But no one has actually demonstrated a real attack with Spectre. I believe that this is an engineering problem, but it is an engineering problem that has important research or implications. So yes, you can do that. There is a question of how we do defenses. There is a question of, we used cache covert channels here, and the reason for that is that we know them, and they are easy to use, and they are fairly robust. The question whether we can use other channels is unknown. Well, we might be able to. So yes, a lot of work here. I don't intend switching areas in the next year or so, at least.
Has Amazon patched its servers knowing they will be 30% slower?
I believe that they knew that it will impact performance. Yes, I don't know if they knew 30%, and it's not 30% in all cases, but yes.
5 to 30%?
I think it was 5. Yes, they said 5 to 30.
Yeah, some places got a bit more than that. I think it was the game developer recently released statistics on their servers, and they took 50% hit performance, which translates to them as requiring twice as many servers to run their game. So overnight, their costs doubled. They were not happy.
Do we have any other questions? This is one of those loud talks, I think. This has been big. I can't but admire the elegance of the research that went into finding these attacks. So if there's no other questions, please do join us for lunch today, Yuval.
Thank you.
Thank you very much for a fascinating presentation.
Thank you.
I'm just going to stop the recording.